All right. A little bit of attendance. 1, 2, 3, 4, 5, 6, 7. Something. Marco and Dawson. All right. So I was thinking about assessment stuff just a second ago, and I think it would be wise for us to have a little bit more assessment to do with that forces in motion and energy and momentum stuff. So I would start planning for that if I were you. Let's have something like that will take place towards the end of next week. So let's say maybe Thursday. All right. So I'll send out a file that you can think of as a test for forces in motion and energy and momentum. Okay. So we'll schedule that for Thursday. Any questions about that?
Will it be one that we can do like after class, or is it going to be like an in-class thing?
I'd prefer it to be after class.
Okay.
Yeah. Otherwise, take up a lot of class time and not get through things that we want to make sure to get through. So I don't want it to be something that I'm not going to be giving it to you way in advance and you have forever to think about it and ask for help and work on whatever. It's a little. I'm going to be giving it to you on, let's say I'll give it to you on the Thursday and it's due, I don't know, like I'm thinking maybe that Thursday night. So you think of it as like you're doing this thing in a sitting as a test, if that makes sense. A little bit more like an actual test rather than, now obviously I can't police how you go about it. I don't feel like I can anyways. Maybe I should be pretending I can. I don't know, whatever. But yeah, I'll send out a test for you to do on Thursday in the evening, whatever. Does that make sense? So hopefully it works out that the lesson homework to do with that from that day is pretty light. I'll try and make sure that works out to be the case. There's some that are coming up where it's like just lots of neat concepts and we're not going to be doing the nitty gritty math to do with it. So it should work out. All right, so here we go. So of course, continuing our journey on investigating nature of light. So particle versus wave nature of light we're talking about there, of course. And so we're going to start to look at destructive interference a little more specifically for light itself. So just as a reminder of what we already know to do with destructive interference with waves, obviously pretty quick analysis here, but we know that we can have two waves that are in the same direction adding up. We call that constructive interference. They add up temporarily while they're overlapping, and then they both continue on their way, as we've seen before. So just like you saw before, it's like deja vu, maybe. You've seen that before in grade 11. And then the bigger one we're interested in is destructive interference. And we know that if we have an up pulse and a down pulse combining, we noticed that they canceled out. And then the red one kept going and the green one kept going. So we know that waves do this. They constructively and destructively interfere. I mean, yeah, like that's totally review, obviously. So we also looked at two-dimensional waves. So those are very linear, just one-dimensional waves, right? Forwards and backwards only. The two-dimensional stuff that we did is going to apply as well. So if we had two-dimensional waves going out, we have crests and troughs going in circles like that. We found that we ended up with this nodal lines, like an interference pattern of nodal lines and antinodal lines. And that was really like, we called it, we recognized that it was really a standing wave going on. And so there were spots where there was constant destructive interference along those nodal lines, the blue ones, because you've got a crest and a trough arriving, and then a little while later, a trough and a crest arriving from, this one radiates out to there, right? So we just basically reminding you that this is something we've talked about before. So, yeah. So go back to the slide in the previous lessons of close up. Actually, I have a better picture of that now. I managed to get a better picture of that pattern. So let me find what lesson that's in. I just forgot to add it into this slide here. Single slit interference pattern. Yeah, it'd be in this one. Yeah. Let me just grab that picture, and we'll see it again later in lesson 59. But whatever. Might as well grab it. It's because some people I know saw the interference pattern between your finger and your thumb. It's very much not explained yet. Of course, we're going to explain it really well in this lesson when we get to it. But that is the picture that I wanted to. Let's grab this whole slide here. I'll copy and paste, hopefully. So let's go. More explanation to come, and so on, whatever. So let's. I just want to just do this as a separate page, maybe. Undo. Bear with me here. Undo. There we go. New page. All right. So I'm saying, like, go back and look at that thing. What we saw between the fingers. Not only did we see diffraction, we saw like the darkness because light wasn't getting there. But if you look close here, you can actually see, at least on my screen, I'm not sure how good of a version you're getting there, but I'm going to circle it. So basically, I'm going to circle it, and then I'll get rid of my circling. But you can see a little band there, and then another little band there. Can you see that on your end? You can see it in the edges of that darkness. You can actually see some of those bands. Now you can see it better in real life because, of course, the human eye is better at capturing low light, difficult to see things. Like it's the human eye, it's better than any camera. But managed to actually catch it in that one. Can you see it? Yes, someone answer. I'm assuming you can. I don't know if it's the same quality on your end.
Yeah.
Slightly.
Yeah, it is. Like I just was super happy to have captured it at all. But you can definitely see it better in real life if you try hard enough, basically, and look at it hard enough, as they say, whatever that means. So yeah, there's actually a bit of an interference pattern. So how is that possible with only one light source, one slit? We're kind of ahead of ourselves a little bit there. So what I'd probably write this as for now is like, hey, there's actually an interference pattern there, and we're going to eventually get to that. Okay. For now, we're going to look at interference patterns that are easier to describe. So this is one that I would do in 124 very easily. I just have a bunch of film canisters and some soap film it's like glycerin and dish soap and whatever mixed with water, and you get the right ratio, and it makes really nice soap films. But really, dish soap and water works pretty much anyways. But when you do get a soap film and you start looking at it, what we have here is it's dark in behind here, right? And so you're not seeing anything coming. You're not seeing the inside of the film canister. You're just seeing the light that reflects off of it. So just like when you've seen other partial reflections and partial transmissions and that, typically people focus on the light that's transmitted through rather than the reflection. Here we're focusing only on the reflection. But we're getting sections where there's like bands of interference of different colors and everything else, and we're gonna talk about all that very soon. But we're looking at destructive interference, especially this top section is really dark because the light that's reflecting is destructively interfering, and I'll be showing you how and why very soon. So if you this is kind of what it looks like, a little bit easier to picture. So that's the film canister, And then this top section here actually has soap film there, but you'd swear you stick your finger through it because there's no light reflecting, which is exactly what would happen if there was no soap film there, right? So you can see soap film here, and you can see the reflection of the cabinet and the countertop behind it, and so on. But you can actually, and depending on when you look at this thing, you'd see those little bands of interference patterns as well, which we're almost getting ready to explain. But that top section, where did I go here? Yeah, actually has soap there too. And so if you, I don't know if I poke my finger in there at the end or not, but if you did touch that, it would pop the soap bubble, which is a good way to sort of show that there really is soap there, but I didn't do it in that video. I've done it lots of times in person, but anyways, so this is a picture of it, as well, and all these different pictures of it. So we're looking at trying to explain interference patterns on films of soap or thin film interference patterns. That's what we're talking about. Okay. So we are going to analyze this out. This is a picture of the soap film here, and this is the film canister. And so you want to picture the soap film being thin at the top, and then it bulges out to thicker at the bottom. And that's going to be part of our complete understanding of like why we get these patterns in horizontal lines. So this is a certain thickness, and then it gets a little thicker, and then a little thicker, and then a little thicker. Okay. So here we go. We have light coming in to a soap film, and I'm going to add in a little bit of information here. This would be like air here, which is fast velocity, right? And you can think of it as like a light material, fast velocity. Then this is soap in here, which is going to be a slower, right, or a slow velocity of light. This is a light, of course, velocity of light in there, and then back to air again, of course, right? So I'm just pointing that out because that's sort of a key part of the analysis. That as well. I was going to make it stand out. I was going to make it purple just to stand out, but who cares? So anyways, that's what we have. Okay. So we want to think about the kind of reflection we have off of this first surface. Okay, if light reflects off of the surface of the soap film, then what kind of reflection is that? Well, there's going to be a partial reflection, right? And it's going to be like it's a fixed end, so it's going to end up being out of phase. So briefly yesterday we reviewed that stuff. Let me just do a quick review of fixed end, free end reflections for you. So just brief review. Fixed end reflections. Let's go reflections. And so we're going to look at fixed end reflections and remind ourselves about that. So we certainly knew and saw that if you had a fixed end, that the wave came back out of phase, is what we saw in the past. Okay, so it comes back out of phase. And when we have free end reflections, we saw this with a pulse on a spring and so on. Now what we had is we had it tied to like a super light string, right? So it acted as a free end, it was free to move. We found that it would come back in phase. Right, so returns reflection is in phase. Now, the other thing I have to remind you of to have this be complete thought here for what we're using it for is that we have reflections from a boundary. So first of all, reflections, we remember that, right? But then we also had reflections from changes in speed or reflections from boundaries. Like material changes we're talking about. And so we would have had a fixed end reflection would be like if we're going from a fast velocity to a slow velocity. Okay, because remember it was very obvious with the spring, it's a slow velocity is the one that's super heavy and so on. And so we saw in that case, I suppose I could have done the pulse as part of that as well, but maybe I will actually do that. Let me give me a second here. Rearrange things a little bit. So we got the fast velocity and the slow velocity. And I just want to add in a pulse here, right? So we have a pulse coming in like this, right? We saw that it would come back out of phase, okay? So it comes back out of phase. So we're saying if we're reflecting off of a slow, heavy material, it acts like a fixed end for very obvious reasons, right? So basically, if we're going from fast to slow, let's highlight this, fast to slow, then it acts as like a fixed end. It's just how it reflects. And also, of course, we knew there was partial transmissions as well, right? But we're focusing on the reflection part right now. So I'll just leave it at that. If you want to add the rest, of course, you could show that we had a transmission as well, of course, right? But we're focusing on the reflection. And then if we had a slow to a fast, talking about the speeds of the waves, of course, right? We had a pulse come in like that, going to a fast material. Then we found that the reflection would come back in phase. And of course it would have also done that, right? But let's undo a little bit of that, too much of it. And even like notice here, like the wavelength got bigger because we're going into a fast material and so on, but the details we're not interested in all the details necessarily at this point. This one reflects back in phase. So it comes back in phase reflection. And so if we're going from a slow to a fast, we're seeing that it comes back in phase, and so it's acting like a free end. Okay, so that's a understanding page that we need from grade 11. So based on that, okay, that's where this information is coming from. We're saying partial reflection, we're going from a slow, fast to a slow. So this is a fast to slow. You can think of the slow as, it's heavy. And so it's acting like a fixed end, and so it's coming back out of phase. So right here, we're saying this is out of phase. Right? That one right there. This one. It's out of phase. And then we know there's also going to be some partial transmission, like we talked about, right? And then the next thing we're talking about is the reflection of that partially transmitted bit. Okay, so there's another partial reflection there. That one is going to be like a free end because it is from the slow material to fast again. Okay, so this one is slow and fast. So it's like it's going into air or going into the faster, lighter material. And so it acts as a free end. And so it ends up in phase. So this one right here ends up in phase with the original. Okay, so we have these two beams of light that are coming out, and they're side by side, and they can combine. If they're out of phase and in phase, then they would cancel out, right? So the two rays end up joining back together. We have an in phase and an out of phase. So if we have, that's, by the way, I should point out that if this is really thin, okay, so this is for very thin film, okay, so this is if this distance here doesn't add any appreciable amount of length. Basically, this is for if this is very thin, then we're saying that they would cancel out, because we just have this in phase and out of phase effect from the reflections only. Okay, so let me change that to be full screen, and I'm just gonna bounce back to, before I leave this for a little bit for you, I'm gonna bounce back to this picture of the, the soap film, and that top section has stretched out to become so thin that there's no reflection coming from it at all. Okay, so it's no reflection at all from the ones once you let it sit long enough. It's so thin that it's going, it's behaving according to this analysis here. Okay, so the purple I've added in there about analyzing like why it's a fixed end and therefore it's out of phase is relying on grade 11 knowledge that we reviewed on the previous page there. Any questions about that? So this is just for the top, that really, really thin section. We're going to keep analyzing the rest of the way, right? But this explains why the top section is so dark and why it looks like there's no soap film there. No one's keying a mic. Do we need this page a little longer or no? No one's saying yes.
I think it's okay.
Okay, perfect. So it's a very critical analysis for us to be able to walk our way through, and we're going to do it a couple more times here, of course. But so that black section in the top, like I've said, is like that's where the film is so thin that we have these two reflections that are canceling out, and so I'm visualizing here that the one reflection is an amplitude that's up, and the other partial reflection, when they meet up, they're it's in the out of phase position, and so we end up with no amplitude at all. That's what I'm trying to show there, is that we have no amplitude of reflection. Okay, because they've canceled each other out. So lots of different ways to see it. That one's not as good. That's a repeated slide. We saw that already. Okay, so here is what I've often heard this described as. So people often say, because the reflected light cancels out, that means there's no reflection, right? So we're reasoning out that that's why there's no reflection. So then the idea is, well, if it can't reflect, then where does it go? What does it do? And when you observe it and look at it, it turns out it goes through instead. So basically, we would normally get a bunch of reflections, right? Like it's just common. We get partial reflections off of surfaces. We're used to it. We see it all the time. Reflections in windows and off whatever, right? Off lakes and so on. We get these partial reflections all the time. If the thin film is so thin, we won't get reflections, because instead the light's going through because of properties of reflection. It can't reflect. If it can't reflect, then instead it goes through. I always found that kind of strange. When it was analyzed like that, to me it's almost like we're living in a computer simulation. You've heard of that little weird theory lately, right? Conspiracy theorists about everything these days. So if we're living inside of a computer simulation, we ended up developing a level of intelligence that's sort of challenging the rules of the game almost. It's like, oh, geez, I didn't think they'd notice or look that close at light. What are we gonna do? Oh, and then the programmer says, oh, let's just make it go through, and so then light goes through. Obviously, that's not what's really going on, but or in my opinion at least, right? But it's observed to be true, and so that's the way it was left for me when I was originally learning this, and I was kind of uneasy about it. I was like, that's weird. It just goes through instead. So we can analyze this a little bit further. We can look at the strange result. Like I said, was all I was ever shown, and so I'm just analyzing this a little further to help you feel a little better about this. All you have to do is think about the fact that there'd be yet another partial reflection, right? And that partial reflection there is going to be a no phase change, and so it's still going to be in the same phase as this one, right? So essentially, these are both in phase. So now we've got transmitted light here, and then more transmitted light here, and so on. So now we can sort of reason out, be like, oh, so we have in phase light coming out the other side, and so we've got constructive interference. We've got a bright transmission of light. I feel like that makes it make a little more sense, but I'm not sure. Yeah, I think it does make sense, right? Because then you can see, oh, it reflected and blah, blah, blah. Anyway, it went. Okay. So again, the same analysis, right? We had this one's out of phase because we're bouncing off heavy, slow stuff, just like waves. And then we've got an in phase reflection here because we're bouncing off light stuff, just like waves, light, faster speed of the wave in the material, you know. And so in phase, and then this one's again bouncing off light, bouncing off of air, essentially bouncing off of nothing, essentially. So it stays in phase with what it just was, and so they're both in phase and constructive interference. So even explaining the idea of why the light goes through so well. So just to take stock of what we're talking about here, we're talking about destructive interference of light and being very analytical about it and predicting and explaining things. Like if we hadn't have seen these pictures, we would have predicted what it would look like, right? What would the top look like if it's super thin? Oh, it's going to get no light reflected. So what's it going to look like? It's going to look super dark, right? So we're doing pretty good. Like, so we're thinking, okay, so that's basically more evidence of wave theory of light, isn't it? That we see light doing wave things, like destructively interfering on partial reflections. So, yeah. So that's where we're at so far. So the next thing I want to do, if no one asks me to pause, I'll get at it. We want to start explaining like why we have different areas of interference. And so picture this is like, you know, that's bright, so it's constructive interference, and then this is dark, so it's destructive interference, and so on. And plus, there's also the color link to it, which will I'll make sense of in the very end after we make sense of just the idea of whether it's bright or dark. So the idea of this is that this section here, okay, this is not super thin anymore. Okay, so this right here, we're looking at like it's not so thin anymore, right? So it's not so thin. So we end up with it being like a substantial amount in comparison to the wavelength. And so what happens is we're going to call this right here and here, we're going to call that the path difference. Right? Path difference due to thickness. Oh, and I should add, I draw these diagrams on angles all the way along. All this one too, you know, is all drawn on an angle. We're really actually trying to visualize light that reflects straight on. And so light that's reflecting straight on. Let me just add a page about this. Note, we are really talking about light that comes in normal to the surface. Note. In order to have it really recombine properly and so on. So note the recombination of the reflected rays is you know, more definite, obviously, or whatever you want to call it, is more definite, is more for light that arrives at 90 degrees to the film, i.e. normal wording that'll get used in some textbook questions and that, so I'll use that same wording here. The angles that we're showing are just to make it a little easier to see. Okay, it does happen at angles too, but it's, you know, it's a little more complicated really to calculate and so on. But angles shown diagram are easier to see. And I feel that's necessary to point out because if I'm talking about the thickness of the film, in this one here, that's why I started to think about it. If the thickness of the film was a quarter of wavelength, well then if you're on a diagonal here, it's not really a quarter wavelength anymore, is it? Right? But we're talking about light that's coming straight in reality. That's what we're really analyzing. Okay, so the analysis changes a little bit if you're going in at an angle, but it still works. It's just a little bit more complicated to analyze. So if we're thinking about a thin film, so let's picture the thin film. So this is the film, and then this is air, of course. This is air, right? If we had light that's coming in, I wanted that all to be black because then I could have like blue light coming in. Feels kind of weird having black light coming in. Get control here. Make that be black. That's just the film and the labels and so on. So I'm going to have light that's, coming in, right? And transmitting also, and, transmitting also, I suppose, right? And then also reflecting and so on. So basically you got light that's coming in, and see how it's kind of hard to draw, isn't it? Right? So you got like light that's coming in and reflecting in both of those regions. Yeah. So picture light that comes in and reflects, but it also goes through and reflects, right? And so on. I don't know, I've just kind of drew the same thing there, but hopefully you catch my drift here, that we don't have to worry about the angles in this analysis, okay? So what do we have here? Viewed at 90 degrees, like I said, but shown at an angle so we can see the individual rays. So we got light coming in. It's going to, I do actually even show the refraction a little bit there because I'm just trying to be thorough here, but it travels this extra quarter wavelength and then another extra quarter wavelength. So if we analyze what we have the fixed end reflection here at 1. So let me put a little 1 there. Right, that's a fixed end reflection, so it ends up out of phase. And then we have partial reflection number 2, which would stay in phase with the original. Notice that the transmitted light isn't out of phase, right? So this light coming in continues to go. It's not going to be on a phase difference. It's this stuff here that's out of phase, right? Out of phase. I'll shrink this down in a second. Hard to write small. Anyway, so that stuff's out of phase, but this is still the regular phase, right? So now it's reflecting, and so it's still the regular phase. So this is would be in phase based on the reflection. But what we're looking at now here, so just emphasize plus here, right? So we have the in phase based on the reflection, but then we also have this extra quarter and quarter, right? So we have an extra half a wavelength, which means out of phase. Just as a reminder, an extra one-half wavelength means out of phase. I'm not sure if that's a question mark or an exclamation point for you. So think about a wave, and you have that's the whole wave there, right? Going from start to finish, we've got a full wavelength. I wanted to get different colors to contrast here. So that's a wavelength, of course. And so then if I had another wave, right, and I shifted it half a wavelength, so I'm going to move this thing over to the 1/2 wavelength mark. So this would be a movement of 1/2 a wavelength. Then I'm going to be moving that red one over to a half wavelength, right? So we shifted over that 1/2 a wavelength. Let me move that up there, right? And so obviously here you can tell we are out of phase. Okay, so right here, out of phase. So that's why I'm saying we want, that's why I'm saying that we end up out of phase now, because we have this extra 1/2. So we're out of phase with what we just were. Notice now that means that these are now both out of phase. Oh, this is now out of also. And I'm going to add in due to the path difference, due to the thickness, I should say. Let's just do that. Okay, so shrink that down. Hopefully we can still see it once I get it small enough to sort of have in there as a label. Oops. There we go. Okay. Okay, so basically now these are both out of phase. So they're both out of phase with the original, which means they're in phase with each other. And so we get lots of reflection. We get reflection. Okay. So we're getting lots of reflection, and we still get some partial transmission, whatever the ratios were, basically like normal reflection. So yeah, the wavelength of light there's that wavelength of light, whatever wavelength we're talking about. Obviously, we're talking about a specific wavelength of light. If we're saying this is a quarter of that wavelength, so whatever wavelength that is we're talking about is what we would see on reflection. And so if it happens to be the wavelength of red light that matches that thickness, then we would see red reflecting. So like I said, we are going to justify why we see the pretty colors. Okay, so if you pick a spot where it's red reflecting, then that's because red wavelength is comparable to this, right? It's 1/4 of the red wavelength. Again, it's all wave analysis to do with reflections, and it works for light, right? That's the bigger picture that we're thinking about all the time. What if we have a film thickness of a half a wavelength? Well, we have the out of phase. I should grab these little labels again here, but oops, that's not where I wanted to go from. This one. So that out of phase is still going to apply, and then I'm going to have to change the wording of that one, I expect. So let's paste that on there. So this one, I'm going to change the wording in a second, but this one for sure is still out of phase, right? What happens with this one now? What's the wording I'm going to have to put in there? Well, we have the free end, certainly, to do with the reflection, the partial reflection number 2. Oops. Partial reflection number 2, partial reflection number 1. So that's analysis is still good, right? But then now we have an extra half and an extra half, which means it's just we're a full wavelength off, right? So that's just going to be the same phase as it was, right? Being a full wavelength off. I suppose I should make one of these pages to do with that, right? So I'm just putting after the slide because that's when we realize we need to talk about it, right? So an extra full wavelength, or any multiple, 2 of them or 3 of them or whatever, means instead of out of phase, it means in phase. I should get rid of all of it, otherwise I'm saying in of phase. All right, so it means in phase. Oops. Pen. Right, so it's going to be in phase because if I move this thing a full wavelength over, this pattern, of course, would have kept repeating because that's the idea of waves in general, right? So now we're going to say in phase there. So we're moving over a full wavelength now too. So let me just redraw that one. So we've got the red one moving all the way over here, which is a full wavelength over. Yeah, full wavelength over. And so now we can point out, yay, it's in phase. That's supposed to say phase. It got messy. In phase. Okay. So that's the analysis for the half thickness. So picture this film that I talked about a long time ago up here somewhere. Talked about a thin film, and I showed a picture of the bulging thickness of the film, wherever that was, probably in this slide. Right? Where when it's a quarter of a wavelength, we got dark, and then when it's a half a wavelength, we get bright, and then we get multiples. That just kind of repeats. Okay. So it turns out actually you think of it as odd multiples of a half. So let me go to that slide here. So half, and of course, and any odd multiples of half, right? So odd multiples of 1/2 wavelength. And then this one would be, of course, any even, any multiple of full, right? So any extra n, where this is a whole number, an integer value, whatever. So we're talking like 1 wavelength over, or 2 wavelengths over, or 3 wavelengths over, etc. They all produce in-phase stuff. And so we get this alternating light and dark. As the film thickness increases, it alternates between light and dark and so on. Okay, so apply that same analysis to your thumb and your finger. Sort of, you're gonna obviously think of the details. We're gonna see the details in more detail later on, but yeah, so that we're alternating between light and dark there for different reasons, of course. So I'm vaguely alluding to hey, that kind of makes sense here, but there is still some detail to be described. Cool. So you get the idea of this? The thin film reflections are neat. They're very predictable. So we end up making accurate, correct predictions about light using wave analysis. And so it builds confidence, of course, in our wave model of light. That's why we're looking at it. So an application of this is right here, right? So, you know, anti-reflective coatings on glasses and lenses in general for binoculars and microscopes and so on, right? Remember, if the light reflected destructively interferes, then there's no reflection, right? So this person has essentially paid more for these lenses than her other pair of glasses. It's the same person, I guess, right? So this is just what it looks like if you have a reflective coating, or if you have reflections, I should say, off your lenses. And this is what it would look like if you have an anti-reflective coating, right? So these anti-reflective coatings is just a thin film, right? So this is it's a thin film. And what they do is they make it equal to 1/4 wavelength, and they just pick like a sort of a central, you know, mid-range, mid of range of visible light. Oof. Mid of the range of visible light. And so it does a good job at reducing the amount of reflections of a particular wavelength, of course. But overall, it's still going to reduce things a lot. It's just a percentage, which should be a fairly tricky calculation to work out. But okay, so that's anti-reflective coatings. It's actually just a thin film. So it could be 1/4, right? Or of course, maybe they don't have it that thin, or it would be 3/4, etc. Right? Whatever thickness is easy to engineer and apply to the lens. I'm under the impression it's this 1/4, but who knows? It's pretty thin. So what that looks like is, of course, you know, the lens coatings on glasses in general, but it's just a slide dedicated to binoculars here. So picture this thin coating on here, and you've got this reflection that's out of phase, and then this reflection that's in phase, and so on. You know, this is if they're both fixed end reflections. You know, so the lens is the highest index of refraction. We'd be analyzing that we'd have an out of phase reflection from both, and then the 1/4 and the 1/4 would give you the opposite phase, and so the reflection would cancel out. If you look at a pair of binoculars, that's a good pair of binoculars, and you look at the reflection, you're going to see color on the lens. If you look at a really cheap pair of binoculars from like the dollar store, you probably won't see a color on the reflection. You'll just see reflections that just look like normal color, because they're not engineered. They're not designed to have a nice coating that gets rid of a certain wavelength. So purple and red and even green, depending on, you know, what that company has chosen for their thin film. Different companies prefer different, you know, they market themselves differently or whatever, but that's why you see the color. You get that particular color is reflecting, and then the rest is going through really well, right? So. I should mention, by the way, the goal was to stop there from being reflections. This one, I just got off track a little bit. This one, the goal is to let light go through, right? So basically it allows the blue and the green to go through really well, because it's, you know, just the red's reflecting, if that makes sense. The other thing you can get with glasses, by the way, is an anti-reflective coating like this on the rear of the lens. So my glasses have this, and so I don't see reflections in my lenses from a light that's behind me, just because I have that feature on my lenses. I always make sure whenever I'm getting glasses, like, it's got rear anti-reflective coating, right? And they're like, yep, we're good. On the front is good too, so it doesn't look as weird, right? You don't see the reflections when people are looking at you. They see your eyes rather than a reflection. But the rear one is the one that's important for me wearing the glasses. So this is just a page that talks about, those different colors, right? So if the red is reflecting or if the yellow is reflecting, you're going to see the different colors, right? Another application that you'll see in real life, right? What's causing these colors? Well, we've got a thin film of gasoline, right? So the varying thickness, layers of thickness, I'm assuming it's probably thickest here in the middle of where the spill was, and then it spreads out thinner and thinner, right? We're getting different colors of light destructively interfering and allowing other colors to reflect, and so on. So physics is all around you. So here's just a worked example. I'd recommend this right here. Draw a diagram, right? This stuff that we've been doing where we have the film and the air and the glass and so on all written out. It's a lot easier to reason out the thickness of the path you need and so on if it's easy to keep track of the different phase changes. So this textbook example needed some help. They didn't tell the index of refractions of the coatings, but then in the solution they have them, they're using them. So I put on there at first, I put, that they'd have to tell you whether the coating has like a higher index of refraction or a lower index of refraction than glass. So it's the way they've done the numbers is if it has a lower index refraction. So we've got this material is the fastest, and then this one's slower than air, of course, because everything is, and then this one's even slower than the coating. So these are both fixed end reflections as a result of that analysis. So that one's out of phase, and that one's out of phase. Right? So they are in the same phase as each other. And this was, the question was, we want to minimize transmitted light, which means we want to maximize reflection. You have to just pay attention to what they're actually asking, right? So if we want to maximize reflection, we want them to be in the same phase as each other, which they naturally are based on the reflections. So what I'm saying here in my analysis is that the path difference doesn't need to change the phase, right? So we don't want a 1/2. We want this whole thing to be one wavelength, right? The total path should be one wavelength or 2 or 3, but the thinnest one's going to be half of that. So you get a half here and a half there. So now it's out by a full wavelength, same phase as it was. So they're both still out of phase from the original. They're in the same phase as each other. Right? So that's the analysis, the ideas of it. They are asking for what thickness. What thickness do you actually need? So in order to get that actual thickness, we know the thickness is a half a wavelength, right? So first we need to get what the wavelength is in this. That's why we need the coating, index of refraction. Okay, so review, this will be to do with what you did yesterday with yesterday's lesson there. So if we're going from air to the coating, right, the index of refraction air to coating, we're looking at the wavelength of the light in the air over the wavelength in the light of the coating. So they've told us, right, this is the wavelength of light in air, the 568. So you're going to see 568 plugged in for the wavelength in air. You're going to see the wavelength, or the index of refraction plugged in, and you're going to solve for the wavelength in the coating. And then, of course, figure out what half of that is. So here's the fixes. They had it all messed up. I think the authors just kind of got lost track of what they were asking, basically. But we're saying we want constructive interference, right? So the two reflected rays, therefore, want to be in phase, right? And so for constructive interference, you want this. We don't need to change the phase, like I said. So this, if we did the number version of way I like to do things here, we'd have the 1.4 equals the index refraction, or the wavelength in the air, the 568 over the wavelength in the coating, and of course algebra leads to that. They just do the usual solve for the variable first business and then numbers in. So now that we know the wavelength of the light in the coating, then we can say, oh, okay, so half of that value is the thickness we need. I just fixed the textbook error there to be what they actually asked. They answered as if they wanted no reflection, I guess, or I don't know. It gets confusing whether you're talking about having no reflection, therefore the transmission, or whether you're having lots of reflection, therefore there's no transmission, and kind of mess you up. So I feel for them. Do we need anything more here?
Just a minute longer, please. Sorry.
Let me, since you want that, let me put it back so you can see the whole thing. I'll add in, basically it's like first we're doing this, and then to make it more clear what's happened here, then we get the thickness based on the fraction that we know we need.
Okay, that's good. Thank you.
To go G2G. All right. So another neat application of this. CDs, DVDs, Blu-ray players, and so on, they actually operate on this principle. So you have a layer of foil, and then you've got another reflective layer on layer of foil. Actually, sorry, you don't need another reflective layer. But basically, I think you probably do actually, because it burns a hole in the foil, and so it's actually going to be reflecting from the bottom. But the way I have this written is good enough, basically. Maybe there's two layers of foil, basically. Anyways, if you have light coming in and reflecting off of that, and then you have light coming in and reflecting from here, if this is 1/4 wavelength thickness, then basically you can see that the light is going to alternate between basically in phase and out of phase, right? And so you're going to be able to get the laser beam that's coming here to pulsate on and off, because you can get in phase reflections and you can get out of phase reflections happening, over and over again in a code, and of course on off ones and zeros and so on is what binary code in computers is, right? If you have an MP3 of your favorite song, or you have a picture, a digital picture file, it's really just a bunch of ones and zeros. And so CDs, DVDs, Blu-ray players, optical hard drives, all of it work by just pulses of light that go on and off to read the code. That's an actual microscopic view, probably electron microscope by the looks of it. Make sense? That's an application of our wave knowledge of interference properties with light. So neat, I think. All right, so this is actually the same stuff. It's just we're going to look at interference patterns and air, like basically a film of air. And this analysis here doesn't have the varying thickness idea, whereas this, now we're going to talk about a film just of air instead of like soap film or whatever, varies in thickness. So let me go back to full screen here, full view or whatever. Page width. All right, so picture a piece of glass, and another piece of glass that are like forming a little wedge in here, right? So when we look at what happens, light coming and bouncing off of here is bouncing off of air. It's bouncing off of a faster velocity, speed of light in it material, right? So that's like a free end, right? So it's bouncing off the faster material. So it's like a free end. So it's going to be in phase. It's going to have no phase change. Then the light goes through the air, bounces off the glass. Well, that's bouncing off a slower material. So it's like a fixed end. And so it's going to have a phase change. And so it's going to be out of phase, right? So based on just the reflections, we're probably at 8 now, aren't we? Based on just the reflections, these are going to be in and out of phase, right? One's in and one's out. Now, plus, of course, we have to consider this path difference bit here, right? So plus that path difference effect that we're going to have, here and here. I should use my pen instead of my mouse because it's really hard to write properly with a mouse, right? So that's that path difference stuff. So we have to think about that path difference effect. And it's basically the same as what we've done, right? So the increasing width along here, of course, causes this to alternate between bright and dark. And so you get a bunch of bright and dark bands. So this is what it actually looks like. If you have two glass wedges, two sheets of glass with something here holding it apart, then you get a wedge of glass, and the interference effects caused you to see little lines, the light and dark lines. Okay, so those light and dark lines can actually be used to measure a thickness. We're going to see that in a bit. But if you're looking at, this picture, two pieces of glass, and then what's held apart on one end, what you'd be seeing on the surface of the glass looking down from above would look just like this. Okay, and there's an actual picture of, with a magnifying glass on there to help you see it or whatever, but that's what you would see. So our goal is to be able to use this, right? That's the fun part about physics, is it allows you to actually use math knowledge and science knowledge. So we want to be able to use this, and what you can use it for is to actually measure this thickness. So that's shown on this next slide here. And so essentially the same picture, but just analyzing more in one spot. So you can use this to measure really small thicknesses. So if you put a human hair in one edge of two pieces of glass, and so you have it pivoting here, and you've got this little air wedge, shine whatever frequency of light you want on there. A lot of times people use like it's like purple or even UV, but it has to be something you can see. Obviously, it's usually high frequency light we use. Anyways, you're going to get all these little dark and light fringes. And so the deal is that the light and dark fringes, the spacing between them is fairly easy to measure accurately, because this piece of glass can be like 10 centimeters long or something. And so you just count how many fringes there are, and you'd be like, all right, so there's how many spaces actually you're looking for. I'm going to be clear about that when I do the numbers. But how many spaces there are, take the total length, divide by the number of spaces, and you've got, the space difference, right? Space length. So if it's 12 fringes, just note that would actually lead to there being 11 spaces, right? So that's what we're going to be calling like delta X eventually. Just as an easier set of numbers, picture like 4 fringes, right? So we have 4 fringes. And that's the same as, unless they mean, I'm not sure the author, if they say fringes, do they mean spaces? I'm pretty sure, like I'm doing the numbers where it's like the spaces. I'm just not sure of the meaning of this word fringe in their language, because I corrected one of the homework questions, but maybe they mean spaces when they say fringes. I don't know. So this is 3 spaces, obviously, right? So that's why I knew it was going to be 11 spaces. If there was 12 dark bands, which I believe that's what fringes would mean. I'm just wondering if the authors in the textbook take it meaning differently. So these are dark bands, right? So 12 dark bands would mean 11 spaces. So don't worry about developing this. Follow along. And what you're going to get is you're going to get a new equation that's going to be on your equation sheet that you have access to. And even if there's like 73 variables, which there isn't, you plug in 72 and you solve for the missing one. It's the first level of types of problems we're talking about here in the vast majority of these questions is take the equation, plug in the numbers you've got, solve for that missing one that you don't have. Okay, so don't stress out about these equations. Just know that you are going to get practice using them. And overall, the bigger picture is build even more confidence with this wave nature of light. Because we have all this wave analysis and it's leading to awesome predictions about light. So just to develop this equation a little quickly here, we've got a triangle that has like an x1, a lambda over 2, and a whatever, right? And we've got an x2 and a lambda and a, distance there. The big one is the total length of the glass, which is clearly something we would measure and know. Like I said, it could be 10 centimeters long or something, right? And then we have this unknown thickness, this t. So this triangle ABG is similar to triangle ADE. They used the wrong symbol here. Similar would just be this. So if you have an equal sign with a squiggle, that means like congruent triangles, which means more. So I'm just gonna undo that again. Let me just go nice big one like this. It's really just that symbol. And so by similar triangles, similar is this, right? So these triangles are similar. If you want to analyze that, they certainly have the same angle here. They share that angle. And then we only need another angle the same. Just thinking of the math analysis of this. The way they show, it doesn't look quite like these angles would be the same, but it's because we're not talking about perpendicular light. So I think we can just analyze it as angle similarity, but who cares? It's not a math class. So if you trust me that these are similar triangles, then that means that the ratios of sides are the same. So similar triangles, I'm just going to add in here, ratios of sides are the same. Right, that's why we're interested in these triangles being similar, because it guarantees that the ratios of the sides are the same. So we can say x1 over x1 in comparison to L. So we're doing the two bottom lengths. So x1 over L, which is bottom over bottom, right, is going to be the same as angled side over angled side, lambda over 2 over the t. So they did a between triangles ratio from triangle 1 to triangle 2. It'll be the same as triangle 1 to triangle 2 in the corresponding sides. Okay, so that's just equal ratios of sides. So basically, you can figure out the x1 value from that. We get, just solving, multiply both sides by L. So L times lambda, we write algebraically. Are you okay with the algebra of that? This would be equivalent to L, how do you want to write that, times 1/2 divided by the 2. So basically, divided by the t, sorry. And so that would be equal to lambda over the t times 1/2. And so that's how the 2 is getting to the bottom. Anyways, so x1 is L lambda over 2t. The other triangle here, the ACF triangle, is also similar. So by the exact same logic, we've got x2. Same deal, right? So I'm just going to put it in the exact same orientation here. Make it nice and easy to follow. So remember we talked about how the distance between the dark bands, like picture on here, you're going to be getting a dark fringe here and then another dark fringe here. And so if we have these numbers, you can actually get the spacing between these is what we're looking for. Right, so we've got the x1 value and the x2 value. Now you have to remember, things are kind of distorted here because we're exaggerating the size of this space, right? So this number here is the same as this number here when this is a really small value. So it's a bit of a, and that's why they don't look like similar triangles, by the way, too, here. So basically, the thinner this thickness, the more similar the triangles are. So this works well for thin separations, thin wedges. So we are interested in this delta x thing. So it's x1 take away x2, x, always just 2 take away 1 final minus initial, right? So x2 take away x1, blah, blah, blah. Common factor out the L lambda over t. You get a 1 minus a half, which is a half. So this is a formula that we can put on our equation sheet. And we can use it to, if we know, I'll have to erase all this in a second because I'm going to copy it to our equation sheet. But if we can measure this nicely, right? So this is measurable, and the length of the glass is certainly measurable, and the wavelength of light you're shining, you can pick what wavelength you're going to send on there. That means you can figure out the thickness of that human hair in that picture that we were just talking about. Okay, so let me grab our equation sheet. Course files. I do it right now. Course files, equation sheet. Go back to that while we're waiting in case you're trying to write stuff down. But like I said, it's just the usual, like plug in this case, plug in 3 variables, solve for the 4th one, right? So let me just kind of do this. I'll leave that part, I suppose. Yeah. All right. And so you just keep track of like what it's for and on your equation sheet, and you refer to it when you come across a question like that. Nice part is for you, for this course at least, I'm not requiring you to worry about trying to memorize these equations. I just want you to understand what they mean, how to use them, where they come from, you know, just understand what they mean and be able to use them, and I'm happy. So I'm not going to be requiring you to work without equations. At some point, if you go on in physics, you might have to in a course, but it's frustrating. I even when I was a student, I was the same way. I was like, why do I have to memorize this? Like, I'm good at using it. Maybe not as good at memorizing as I could have been. All right. If I was good at memorizing, I would have become a biologist. Sorry, can't resist. Just can't help myself. All right. So this is what a question looks like. So immediately when you see this in a question, air wedge, you're like, oh, I know. I need to use this thing. And just paste it because it was still on my clipboard, right? So use your equation sheet, use it, put it in, right? So they actually gave us the t value, which is typically not the way this would really work in real life, right? Usually you're using it to measure thickness, but anyways, and they're giving us that this thing's 11 centimeters long. So the microscope slides are 11 centimeters long, so that's your L. And then they gave us the thickness, they gave us the wavelength, and now they're asking like to predict what the spacing of the dark fringes would be. So it's just not the typical example where you'd be solving for the thickness, but that's typical with textbook authors. They aren't necessarily thinking about what people would really use this for, unfortunately. But the numbers, like I said, just plug them in and solve it out. The only nice thing is algebraically, it's the exact formula, of course. You don't have to rearrange at all. Plug in, calculate. So a little bit of a loop they throw a little bit of a curveball they throw at us here is they ask in part B, hoping you're ready there, let me know, how would the spacing change if the wedge was filled with water? So instead of being an air wedge, it's a water wedge. How would things change? How would our analysis change if it was water instead of air? Now, assuming, which we know is true actually, that this is like 1.52 and then this is like 0, but now it's going to be, if it was water, it'd be 1.33. We still have it going into a faster material. So all of the analysis still applies. Everything still works. The only thing different, it's actually kind of a silly, trick question, if you will, if you want to think of it as a trick question, but the only thing that's different is going to change the wavelength, right? Instead of it being 663 nanometers, you're going to have to figure out the new wavelength and then just solve. So here I put it where it's like, well, there's going to be a new wavelength, and so there's going to be a new spacing. So get what the wavelength is based on your work from yesterday to do with index refraction, Snell's law, and just calculate what the spacing would be. Again, exact same calculation, it's just different wavelength number. Okay, so it's not as tricky of a extended question as it might have seemed when you first look at it. So a new formula to refer to on your sheet, just a new situation to recognize. Oh, we got an air wedge. We have a wedge of something. Looking for spacing of the dark bands. Use the formula. So that's it for that lesson 55. This does have the analysis from a different source. So you can see the idea of like the waves are in phase and out of phase and so on. You can certainly look through it if you wish. I've certainly delivered it already though, and they talk about the idea of the reflection off the glass and just like I did there, just to add that into my lesson officially though. The idea of in phase and out of phase when you're reflecting and so on. It's all there. So that stuff is to do with that. So the next lesson, luckily, is just kind of neat. It's not as big on new equations and calculations and so on. So it's just a little bit more of a concept lesson. So it won't add as heavy of a question set to make sure to be able to do for when we have a test assessment assignment type thing for this section. So just keeping stock here, evidence of wave nature of light. We've got destructive interference recently. We've got partial transmission, partial reflection. We've got refraction. We've got diffraction. We've got like all these things that wave nature is totally able to explain because waves do it, right? Particle theory has some trouble explaining these, right? So obviously we're leaning towards thinking, geez, there's definitely a wave nature of light. So the logical next question for us to think about is, what kind of wave is it? Is it a longitudinal wave, like a pressure wave, like sound, or is it a transverse wave, like water waves, right? And to do with this question is why we're looking at polarization. Okay, so just to phrase the, what we're looking at here, you could obviously just make, if you're trying to have some kind of notes down, you're going to say like, oh, so what kind of wave is it? We've got lots of evidence of wave nature. What is it, longitudinal or transverse? So here we go, right? So details of the type of wave. We actually already talked about how it's really an electromagnetic wave, right? So eventually we're going to see, this familiar thing where basically, let's put it this way, you're probably not too surprised to see like a sine wave that it's transverse because we've already kind of talked about that. But let's go through the details here in this version of this topic. So James Clerk Maxwell person who itemized out or figured out Maxwell's equations for electromagnetism. Definitely one of the greatest physicists of all time. I agree with that. Stumbled upon this discovery, right? Basically, when he was looking at electricity and magnetic waves and so on. So way back in 1860, right, the relationship between electricity and magnetism been established, but was still being looked at a lot, right? Maxwell had theorized, right, that that a wave created by a changing electric field with a changing magnetic field as well, right? They, just theorized that there'd be a wave that would permeate out from those. And then he noticed a clear connection to light as well. And so basically he found that what that speed would be, right? So basically he found this speed was literally the speed of light, right? So when they studied the waves coming off from electricity and magnetism, they various forms of it, which you'd think of as like microwaves and radio waves and so on, right? If you're trying to keep track of all of the things we've talked about in the past, the electromagnetic waves have all these different types. They were working with a different type than visible. Ended up determining the speed of light was the speed, and we're like, oh, okay, so I guess light is an electromagnetic wave. That's the idea of it. This page isn't necessarily great at emphasizing that, so I'm trying to help there. So he had these 4 ideas. I'm just going to show these quick because it's really not that big a deal, but we know that electric charges create electric fields. Yeah, we already talked about that in the sequencing of lessons that we've done. The fields begin and end on charges, going continuous loops, who cares? The changing electric fields produce changing magnetic fields and vice versa. We already know that from our electromagnetism. It's not critical for our understanding of what we're looking at right now. Okay. It's just maybe the idea that this change produces that one. It's like there's a wave, that's happening between the two of them, right? So he concluded that what do we have here? As an electric field is created, changes the magnetic field, and so on. Yeah, he's the one that theorized that they're perpendicular to one another. And like I said, calculated that they'd be the 3.0 times 10 to the 8 meters per second. Then it matched the speed of light. So there's that conclusion I was getting to on the other page. And so this is the picture that I was searching for a second ago, where I was like, you've seen this before. We've got like an electric field and we've got a magnetic field. And so this is what he started to visualize as light. Because after studying other forms of electromagnetic radiation and finding the speeds were matching, be like, well, obviously light is really a electromagnetic wave then, isn't it? Okay, so we're picturing right away, I guess, then, that light is a transverse wave, right? So I'm not supposed quite there on the sheet yet here on the pages, but we're basically there. So the cause of electromagnetic radiation, we know it's disturbances in the electromagnetic field, right? So this little applet was pretty cool. Doesn't work anymore, but I used to be able to like move this positive up, and as a result, later on, after the signal gets here, this one would go up, right? Because it's attracted to it. And then if I pulled it all the way to the bottom, this one would fall to the bottom. And it was like spring loaded. So I pulled it up and let go, it would bounce back and forth, which would then of course cause this one to bounce back and forth. And so we've got action at a distance, we've got field theory, right? So we've got an electromagnetic wave that's transmitting that electromagnetic field information. Okay, so the idea of this up and down vibration, and then the velocities, perpendicular to that, definitely anchors this down as a transverse wave. Okay, so where do I end up saying that? Do I say that somewhere? Like I should have concluded that already, I guess, here even, right? So it's a transverse wave. I think it's written somewhere, but it's not jumping out at me. So transverse wave on there, and of course transverse wave even here. You can picture these directions and these vibrations, wherever it's best stated. Okay, so because we've got the vibration this way, but then the direction of the wave is perpendicular to that. right? The V is at 90 degrees to the vibration. We've got that as a transverse wave. That's probably the best place for it. So the orientation of that vibration is what's known as the polarization. It's the orientation of this vibration. Okay, so that's what we observe. That's what polarization is about. If you're observing polarized light, which is what I want to show you, help you understand. So yeah, we got electrons bouncing up and down. The wave is obviously propagating out at 90 degrees to that because it affects the charge nearby, because we know they attract each other due to the electromagnetic field. So this fluctuation in the electromagnetic field is absolutely the electromagnetic wave we're talking about. Oh, there it is, transverse. I see it now. It's okay to chuckle at me, but emphasis is good. All right, so we've got this orientation, right? Well, here's the deal. Most light isn't polarized, meaning that it's not really just in the one direction, right? So it's very random. The electrons are vibrating random ways, causing random electromagnetic wave directions, if you want to call it that, or the orientation of the vibration anyways, right? So this is what light would normally be. Okay? It's unpolarized, meaning sometimes it's up and down, sometimes it's sideways, sometimes it's on an angle, you know, the vibrations, but all the while it's traveling, of course, this direction. Okay. So the fancy term would be that all of these vibrations here are orthogonal to the direction of the wave, right? So the V of the wave. Orthogonal just means 90 degrees all around, right? So 90 degrees at this angle, 90 degrees that angle, all the way through the 360-degree spin. Anyways, so yeah, so most light isn't polarized, right? For obvious reasons, that it's very random how it's created in that What the Heck is Light video back in the day. We have electrons jumping up and then falling back down a level, and you know the orientations of those could be all sorts of different ways, obviously. So if we have a polarizing filter, we have a Polaroid or a polarizing filter, it'll just let one direction through. Okay, so if you have polarized light, then it would be like this the whole time. So it would be, you know, you'd see this vibration pattern. This would travel, you know, along like this, like a wave. So you picture this section would, of course, bounce down to there, and this section would bounce up to here, and so on. But yeah, that's light traveling through air. That's polarized. Okay. So basically, I just want to show you some neat things to do with polarization. So if we're looking at an actual Polaroid filter, polarization, of course, can be explained if light is a transverse wave, and it allows us to select, right? So if we have unpolarized light, we know that it's going to be up and down, back and forth, and so on at various angles, right? So we have all sorts of, it's not even just those two, it's going to be any angle. All orientations at random, right? So it's hard to visualize that. I could just put this little GIF in there to show it. Maybe copy, paste, shrink, align. If that makes sense, right? So that's what we're talking about. However, best to think about it there. So what we do is we pass it through a filter that only lets one orientation through. And so the one that's vertical is the only one that gets through. And so we end up with polarized light. Okay, so the idea of it is very simple. Polarization clearly is providing strong evidence of transverse nature of the waves of light. So not only are we theorizing that light's a wave, we're also saying like, hey, we can even pinpoint what kind of wave it is. So, you know, it adds strength, adds confidence to the argument or the position. I'm going to show you how polarizing filters work. just for the heck of it. It's kind of fun. So they're actually made of like plastic strands of, it's called dichroic materials, but they're long strands, which is what plastic is, and glass has it too. These long strands, and they get all intertwined. That's what makes things strong, right? So way back in the day, E.H. Land, which is the person who basically led to the company Polaroid, discovered thin sheets of long hydrocarbons, like polyvinyl alcohol, or plastic, in other words, right? For various forms of it. But if you stretch the plastic, it makes the molecules line up. Okay, so that's a key thing, like the idea of lining all the molecules up. And then he dipped the stretched plastic in iodine, right, which makes them good conductors. And what happened, if those long molecules are good at conducting electricity or energy, right, then if light came in this way, right, remember this is like electromagnetic fluctuation, right? So this is like the positive lifting up, and then it would make an electron go to this end. And then it would make it, when the positive goes down to the bottom, it would make an electron go down to that end. So basically, light coming in here, aligned up with it, would make an electron bounce back and forth in the material. And it would, as a result, absorb all that energy. So this is saying light is absorbed since the electrons can move in the direction that the electromagnetic field wants them to move. Okay. The perpendicular version, the electromagnetic field is trying to force electrons to go up and down, but in this case, the molecule is sideways. So electrons can't go that way, so the light's not absorbed. Okay, and then here you'd have like a component, like the electrons can go a little bit, so they can absorb a little bit of the energy, and so you notice that there's some light being absorbed, some light being transmitted. So the mechanics of how Polaroid filters work is actually really simple. You just need a molecule, a bunch of molecules lined up that can absorb the energy of light. So in other words, they have to be able to conduct electricity. They have to be able to get electrons to bounce back and forth. So let's point out that this electron, oh boy, this electron here, right? And then if this was in this field here, we know we've got, it's trying to make electrons move back and forth. Well, then we're saying, yeah, this electron can actually physically go back and forth and get the energy absorbed, right? So that hopefully that makes sense to you. Trust, because no one's asking. We're good to go. So just this page is redundant here. If we have if the molecules are horizontal, then they can't absorb, right? The light that wants to make this wants to make electrons go up and down, right? It's trying to make electrons go up and down. They can't go up and down, so that won't filter the light. Whereas this one is trying to make electrons go side to side, and electrons can go side to side, and so the light is absorbed. It's just the same as the other page, right? So the vertical component, the vertical polarized light can go through because the horizontal strands can't absorb the energy, whereas here the energy of the horizontal components, I'm being more complicated than I have to have here. I should say the vertical aligned light, right? Vertical aligned light. Vertical polarized, I should say, actually. If we use the word, aligning things means polarizing. I'm going to add the aligned in there too, though. Polarized or aligned, in other words, light can pass through because the horizontal strands can't absorb the energy, and then ditto for this one, right? So energy of the horizontal aligned light, or horizontal polarized light. Okay, aligned word in there. It's literally the same as what we did on the other page. So to see this in action is kind of neat. So where do you see polarized light? In photography, for example, you see it. So this picture of a church in Brockville. might recognize it if you're from the area down there. This stained glass window taken by the same camera on the same tripod at the same time, seconds after the other. I, just popped the polarizing filter on and aligned it the way I wanted to align it. And look at, you can actually see the window, right? You can see the pattern in the window and the reflection. This one you can't add because we have a bunch of reflected light. Okay, and so you're going to see in a slide soon that reflected light is polarized, and so I just aligned the polarized filter to absorb the reflected light, which makes the picture look nicer, a little more detail in all parts of the picture. This one here, oh, this video, hopefully it still works here, shows that a reflection off of a floor even is polarized. So basically, see the reflection on the floor, and then see how the reflection's like way less, right? The window, basically the reflection from the window disappears. I'll just redo that. So you can see a reflection of a window, and then it kind of like no reflection of the window. Okay, so things get polarized on reflection. And, it has to do with absorption of energy, obviously, as it's reflecting and so on. Let's just show the details here. So you have light coming in that's, all random directions, but then it ends up polarized a particular direction, right? So basically the direction that the material can't absorb the energies, or however you want to think about it. We're not too worried about the details, okay? But you align the filter so that it absorbs those reflections, and all of a sudden you can see the window, like I said. Another version here, this I don't think will work anymore. I really doubt it. I think it's part of that. Yeah, it's part of that University of Boulder, Colorado website that none of it works anymore, unfortunately. But it was neat. You can move the Polaroid filter here, and you can see what it would look like. If, it's the same as in class if you're looking through a Polaroid filter at say the reflections on the glass. You'll see you can get the reflection to go away. But this was like, the reflection of the sun filtered out, reflection of the sun, or you can see it. So luckily I had screen captured a lot of this stuff before the website went down. Blue light from the sky is polarized. So the use of that is with the Polaroid filter aligned the right way, the blue light gets basically filtered out. Ironically, actually, it's kind of weird. This is actually when I'm reducing the amount of light that comes from the sky. I'm filtering out the blue light, but it's making it look more blue because it's just making it look darker, right? And so the contrast between the clouds. So again, same day, same camera, Polaroid filter aligned and then not aligned with the, in order to filter out the blue light from the sky. And so again, it's just another photography trick, right? This picture would be preferred by anybody and everybody, right? And all it is the exact same camera settings. I just have the Polaroid filter aligned and then not aligned or whatever to filter out the blue sky. So this is what it looks like if you actually just look through a Polaroid filter and rotate it. Okay, so different rotations. This is not, I should make a bit, I'm gonna have to make a better video than that at some point. I don't have the Polaroid filters here, but if it's a nice blue sky day with big fluffy clouds like it was here, obviously the effect is bigger, so that's disappointing. I forgot that video was not the best. So if you're curious, blue light is absorbed and then scattered, right? You've probably heard the discussion about why the sky is blue, right? So white light, all the colors go streaming through the atmosphere. The blue light is absorbed and scattered sideways, and that's why we see blue light coming from the sky. If this wasn't true, the sky would be black all day long. We'd see a big, bright, white sun, and you'd see lots of little white stars, and so on. But all of that gets drowned out by all of this bright blue light that's coming towards us from the atmosphere. Well, it turns out that when that process is happening, that Rayleigh scattering process, it actually also polarizes it. So it's not really, we're not talking too much about that, but basically the other link we could talk to you on, that's more just about sky's blue stuff, right? You filter out all the blue, and you're left with the red end of the spectrum. That's review, but the idea of it being polarized is new. If you don't believe me or have trouble picturing the idea of the sky being dark, if even in the day, if this wasn't true, if blue light wasn't scattered, this is a picture from the top of Mount Everest. And so if you look at the sky at the top in the picture is like almost black. Well, it is black. So it's literally just how the sky looks if you're really high up. And you can see the blue haze from the atmosphere looking out this way. So looking straight up from up there, the sky is darn near black in real life too. Black in the photo doesn't necessarily mean black in real life. This is just Tim talking about being on top of Everest. If you've seen the movie The Bucket List, if you haven't seen the movie Bucket List, then you should put it on your bucket list, I guess, because that's what the movie's about. Things you want to do in your life. Clearly, you want to see the movie. Anyways, yeah. So this is redundant. We've already talked about this stuff. Blue sky is polarized. Big deal. Redundant. I showed this double refraction stuff previously. Turns out that double refracted light is a different polarization. And it's just, you don't have to memorize any of this. I'm just showing it to you because it's neat. So if there's two images, I tried to justify before that you have a double image there, that's why it's sort of blurry. But now I can really show you that double image because one image is polarized, horizontally, and one's polarized vertically. So you can see image 1, image 2, image 1, image 2. You know how they alternate side left and right there. So that's the double refraction shown in a little more detail. LCD screens work on polarization. So if you had a Polaroid filter, you could see the different polarization. The one that I want to talk about a little bit more is this optical stress analysis, because it's such a nice application of this stuff in engineering. So the LCD, like basically you can look through it, but basically voltage aligns the little molecules, and so it aligns them so they're able to absorb or not absorb. It's how you get this analysis is more for like a simple little digital calculator screen, but it applies to LCD screens as well for like TVs, because the dark is just in a small region to block out particular colors of light. So you end up with, you block out the green in area and you got red and blue shining, and so it looks, and so on. The way colors add up, magenta, I guess, right? So the optical stress analysis, I'm excited about it because it's just kind of neat to show you. It's a really cool engineering application of polarization. And remember we talked before about the stresses and strains. If you're pulling on plastic, it aligns the molecules and so on. Because of that, you can actually use, if you look at polarization, you can actually see spots that are under strain. Okay, so it turns out that transparent plastic has the ability to change or twist the polarization of light, and especially when you're putting tension on it. So the amount that it's twisting the polarization of light depends on how much strain it's under. And so polarized light can be used to analyze the amount of stress or strain on an object. So picture like a hook that you have for something, like it could be like the tow hook for towing a vehicle out of the ditch or whatever. If the manufacturer made this hook and they found that the way it was used, it caused the tip to break off, right? That would be bad. Someone gets hurt, they get sued, they lose lots of money. Instead, what they would do is they would know in advance that it would break there, because they would do optical stress analysis. They would make a clear, transparent model of their hook. And then they would put polarizing filters above and below, and they would analyze the polarization of the light coming from and going through the clear thing. So put it on like an old school overhead projector, which I have one of those on 24. I'd normally be showing you that. And you look to see where there's light and dark spots. So I'll be able to show you better in a second, but the bright spots are going to show where you've got stress and strain. So this is what it looks like. Okay, you put them on the overhead, and then you just put a polarizing filter over it. And as you turn the polarizing filter, you end up seeing spots that are bright and dark. And so this right here, that is a strange reality of about the manufacturing process for this kind of little triangle that you get in your set. And the Falcon rule protractors, I just have to Google Falcon rule protractors. They're kind of neat too. I believe I've got that right, but it's not pulling it up for me. So I'm wondering if I have it right or not. Yeah, there they are. So this kind of protractor here, and I wonder if I can get lucky. Optical stress. I just noticed that analysis. I didn't have it in the lesson. I wonder if it'll come up. Yeah, so this is the kind of thing we're talking about. So I'll copy that picture too. But so zooming in on any Falcon rule protractor, including the ones we have in room 124. If you go to the 20, whatever it is here, 10, 20, 21 or 22 degree mark, there's a line there when you do optical stress analysis. It's right there. See that sort of disturbance there. And so you take this kind of Falcon rule protractor. This one's got a stress thing there. It's a little bit of a different machine type thing. So that one's got a stress point there. Let's see if I can get a full picture of the one I really want. That's a, obviously that's a tape dispenser, the other one there, knives and forks, all these different clear objects. See, there's another picture of that triangle, and you got a stress point there. So what you can do is you grab the thing here and here with two hands, and you reef on it, you twist it, you torque it, and where does it break? It breaks right there every time. It's just, that's where the stress point is for some reason in that plastic. And so you can see the idea of like all the stress points on the tips of this wrench pulling on that object there. And so what that does is it allows them to predict where they need to reinforce the object, where they need to make some reinforcements to make it stronger. So with that wrench example, you put reinforcements, make it stronger material or thicker or whatever you have to do. So that's what optical stress analysis does for the world. It allows engineers to analyze the strength and where things would break. Okay, so this area here has a big change in the polarization because there's the most strain. So this is where lots of strain is causing lots of polarization change. And so you can tell this is where it will break first. So I actually did this one year. I have the Falcon rule, the broken one, and then a couple other, some that aren't broken. But one year I said you can do this, and like the class was like, oh, let's try it. Fine, I don't really want to break them, but let's try it. So I just grabbed, like I said, one hand on each side and just started just reefing on it harder and harder until it snapped, and it snapped right at that, right at that mark that we had already looked at with the polarizing filter. So I don't break them every year because I don't like breaking stuff, but the broken one is still in the case, in the shelf, so we can see it. And the other thing that you'll see in life, so this is again seeing things in physics in the world around you, if you have polarized sunglasses, if you have lenses that are polarized, so you can reduce the amount of glare off the surface of the water, things like that, and off the roads even, and whatever. Does anybody have polarized glasses? And if so, have you noticed weird patterns in windows of cars and stuff? Have you noticed this weird kind of hazy, weird kind of pattern? Anybody? No one's keen. I might get a pair of polarizing sunglasses, and then you'll notice weird stuff. These are not calculation based. They're just easy concept questions. The solutions are all going to be posted, so they are not a big deal. Okay, just about concepts that we've talked about. So that is it. I will be PDFing and uploading all of this stuff, including the new equation sheet, which we only added one equation, I guess, two. Is that right? Yeah. Did I forget to add something? I think so. No. Because this one's just analysis, right? All right. Same attendance as before. Yeah. All right. That was a little bit of a longer one, but we got through it. Any questions? Well, enjoy the next half hour of your ministry mandated curriculum time. I can log in at 1 though to help out. So have a good rest of your day. And yeah, it's Friday today. Have a good weekend. Don't forget to submit assignments, and don't forget that we are going to have an assessment opportunity for the motion and momentum and energy unit, right? I'll pick like 3 or 4 or 5 or whatever questions and put it together as a little test assignment type thing. Okay. All right.
I think you're still recording, by the way.
Thank you for reminding me or noticing or whatever. I don't know if I actually did this or not, but